let's get into the first demo. So as I said, there's going to be code snippets on the screen. I definitely suggest and invite you, open your text editor when we're going through this and code these up alongside us so that you're going through it line by line, and this is meant to be interactive. If there's anything that doesn't make sense to you, online or in person, mention it as you're writing it out to clarify. So this should be a really good exercise to reveal anything that doesn't make sense. So we're first working in just the simplest orbital mechanics problem you can, essentially, and working in the two-body model, the two-body problem. So it's a simple equation of motion. It consists right now of just an arbitrary Cartesian right-handed basis vector frame, because we're an idealized model, so this isn't inherently aligned with any defined astrodynamics frame, but it is right-handed Cartesian. It utilizes point mass acceleration with the attractive body at the origin. So as we talked about those two different model types that you can use in asset, this is a simplified model. So we don't have to create a frame. We're not dealing with spice kernels. We can simply instantiate the model. And now we have an ODE object instantiated in one line. We're ready to go and start creating integrators and phases. So a quick overview of what this is going to look like. So this first demo is going to show us how do we instantiate and use the two-body model from Astro, and how do we then use that to model and optimize impulsive delta V's. So we're going to do a demo problem. This is going to be moon-centric because the moon is fun. So we're going to have it be a lunar two-body model. And I've got predefined initial conditions that I'm going to give you guys of a suborbital trajectory. So it starts near the surface of the moon, and if you propagate that trajectory out, it doesn't even achieve lunar orbit. It's just going to do a small orbital hop on the lunar surface. But we're going to want to try and define a delta V that's applied and then is later optimized to attain a specific semi-major axis value that we're desiring as part of this guided example. So then once we've walked through that part together, then we're going to do a time where we take a break, and you as users will try and write up your own code to append a new phase to an optimal control problem that writes a circularizing burn. And then, of course, we'll go over the solutions together.
How are you defining, I guess we'll see this, but when you say it starts off with just a hop, is it just going to be defining a position vector, altitude?
Yeah, we will get to that, and I'll demonstrate that. So we're just, in this case, I'm just going to give you an initial condition that so remember, in asset, your initial conditions need to be the size of your ODE. So your initial condition includes states and time. And if we had controls, placeholders for controls.
Time, then.
Yes, and I'll give you a delta time, I believe, in this example, and show you how do you apply delta times to integrators, since integrators go to global final time, not deltas. So first thing in your script you're going to want to do is do some imports. So let's go ahead, and we're going to take a little bit of time to let you do these imports. These are common imports that you'll find you're importing a lot of in your script. So you'll probably reach a point where you're just copying these imports into any script you write. So first, we're obviously going to import asset itself, but then we're going to break asset apart into a few things. So like we did yesterday, we're going to get vector functions, arguments, but now we're also going to do and vector functions itself. I should have reordered these. We're also going to pull from the Astro library the astro.constants as C. So anything in these examples, you'll see if you see a lowercase c dot something, it's pulling from Astro's constants library. And then because we're doing a two-body model, we're also going to need to import from astro.astromodels the two-body model. Then additionally, we're going to show off at the end of this 2 different ways that you can save your trajectory data. These are just Python operators, so we won't spend too much time on them, but ways that you can save off your trajectory data, and that's going to be useful for the next demonstration where we can use that as an initial guess. And then just NumPy and matplotlib, because we're going to use NumPy for some functions and try to plot things. Oh, did I hit enter again? Okay. Go back a slide. There we go. Alrighty, so now that we've got our imports set up, we're going to do just some model configuration, model setup. So one constant that we'll use a few times in this problem is the radius of the moon. So we're going to just set a variable equal to that, again, using the constants library. So constants.radius moon is going to give us obviously the moon's radius, but it's going to be consistent with the constant library units. So it's technically giving it to us in meters. So once you have the moon radius established as a variable, we're going to set up a model. So remember, we don't need a frame for simplified models like this. So we're going to instantiate a two-body model from the Astro library, which we imported in that last slide. And it expects two inputs. It wants what's the gravitational acceleration that you're handing this model, and what's your characteristic length. So these need to be in the same units. So the acceleration component is using meters, and the length is using meters here. So we're going to do from the constant library, the moon's gravitational accel, the radius of the moon. So what that means is when we've got the non-dimensionalized model, an acceleration of 1.0 is the gravitational acceleration of the moon. So a thrust below that or above that is changed. And any distance, a distance of 1.0 is also lunar radius. So if you are, looking at some smaller amount of length, then it's going to be less than 0 because it's in terms of lunar radii as your non-dimensional units.
200 divided by 2 by 600.
Yes, that's just so well, let's do that now. So now that we've got a model instantiated, let's also instantiate a integrator of this model. So we do, again, just like we did yesterday, we take our instance of the ODE object, dot integrator, and now we pass in the default time. So the default time step here, I'm taking 200 points, 200 arbitrary points divided by the characteristic time of our ODE. So we know characteristic time gets non-dimensionalized to be 1. So now we're essentially saying from the terms here, you've got 200. Your default integrator step size would be 200 points per characteristic time. You can absolutely change this to whatever you need, and recall we're using an adaptive step size integrator. So as long as you are in the ballpark of an appropriate scale, which this kind of doing it relative to your characteristic time is a decent way to make sure you're in the ballpark, then the underlying integrator will take appropriate step sizes as needed.
So mu, c dot mu, and c dot radius moon are both dimensional.
Yes.
You pass them to the two-body from Astro library, which is then going to use those to non-dimensionalize everything. Package.
Yes.
And two-body.t star is what?
It is dimensional time, as it's your unit time, your dimensional unit time. So it's a time in second. It's what you derive how many seconds to be characteristic when you fixed characteristic accel and characteristic length. So when you've got position, velocity, acceleration that have 3 different units. So if you define 2 of them, then all 3 become consistently defined within your model.
Oh, so yeah, you have a length, and then you have some mu.
Yep. So we're essentially, we're in this use case, we're saying here is our characteristic acceleration, here's our characteristic time. From both of those, you can now also back out what is your characteristic distance and what's your characteristic velocity, so that it's all self-consistently non-dimensional.
T star is going to be some 1 over the time or something.
Yeah, it's going to be backed out from your gravitational acceleration term, so the divided by seconds squared, and then we also now have defined our distance So we've gone from essentially meters per second squared and meters given two non-dimensional terms, and then back out from those, what's the actual dimensional time so that we're consistently non-dimensionalizing. So that we don't have to wrap our head around that often or every time we're trying to do operators, and we don't have to keep rehashing that, it's very useful to then define a set of non-dimensionalizing functions. So we want something that is essentially the relative operator of a dimensional unit that we're used to thinking in, scaled to the non-dimensional scale. So for example, with this capital M for meters here, we're going to take the dimensional meter and divide it by what is the dimensional L star of our body that got created. Now we have a method that if we want something that is 100 meters long, but we need it non-dimensionalized, we can do 100 times this capital M. And now we're scaling it down into the non-dimensional scale. So we're going to go ahead and code that up and write that down in your script where you've got meter and kilometer. So again, now we can say, hey, I want something that's 10 kilometers, or I need a radius of, 5,000 kilometers. You can just work in dimensional units and say 5,000 and then multiply it by this term. And now you know the result of that multiplication is scaled properly for your non-dimensional model. So I often do that for, I do 2 for distances. So you do meters and kilometers. I do it for 2 different times normally of day and hour scales. And then you can do it for velocity also, where you're doing meter per second and then dividing it by v star. So you now have a set of tools that in your brain, you can know everything I hand to any of my integrators or phases. I need to hand my initial guesses, my constraints, my objectives in non-dimensional terms, but you as a user can write them in the dimensional results that you want and just multiply it by the scale factor.
And to get an intuition of what this is, like once you put in mu and r, mu, for example, then it's a good idea to just look at T star, right?
Yeah.
And then we get an idea, okay, this is T star, and just check in for human brain, check in what makes some sense in days, seconds. So then when you do any of your integration, okay, this makes sense because my T star was that.
Yeah. Yeah, definitely play around with these to get comfortable with it. Okay. So this next section is we're going to use a function. So recall our ODE is defined in terms of a Cartesian frame. But remember, the problem statement was we wanted to do some burn from our initial condition that targets a semi-major axis value. So that's a Keplerian element. So how do you constrain your Cartesian states to go to a Keplerian element? Well, you can write a vector function that computes essentially the conversion of your Cartesian states into Keplerian elements. So this is fairly long, I know. So if you would like, this is also defined in the user provided inputs.txt in that day 2 folder. Since this is, being able to convert Cartesian states to Keplerian elements is not what this training is focused on. You certainly should know how to do that by hand and analytically, but to not spend too much time on doing this, go ahead and copy this code snippet, this cart to kep conversion function, vector function into your script. And at this point, you should be very comfortable with what it's doing. It's expecting 6 arguments of your position and velocity in Cartesian. It then breaks them apart into position, velocity, and then it just does the standard math operations to define what a Keplerian element is, because all it is a geometric approximation of your states, right? So we compute those using vector functions, and then this function returns the Keplerian elements. So to save time, go ahead and copy that in from user provided inputs, and we'll move on to the more exciting stuff. So now we've got a problem we've got our OCP, our ODE defined. We've got an integrator. We've got some convenience functions. Let's go ahead and set up our initial conditions. So go ahead and set up this section here is essentially just for plotting purposes, is we want to plot the actual spherical moon to know the surface, because I mentioned this initial condition that you're given is going to be a suborbital hop that goes from close to the surface of the moon, and if you propagate it out, it goes close to back to the surface, like this plot over to the right. So go ahead and just code this section up just for plotting. Then here's the initial conditions. I have slightly different initial conditions copied right now, but I'm going to post it in chat so you don't have to go through and do integer precision typing of your initial conditions, or these set of conditions are in the user provided inputs file. I'm going to put it in the chat as well. So feel free to copy it from chat also. You'll notice the one from chat is slightly different from the one in the user input. It's very close to the same. It's got a slightly different eccentricity or inclination value so that it's in a more defined region, but either one of these will work for this example. So in 2 lines, you can just now declare your initial condition. Notice the initial condition is size 7, not size 6, like in some tools. So we've got position X, Y, and Z. We've got velocity X, Y, and Z, and time is part of your initial conditions, because your initial conditions and any resulting time histories from integration are going to return it to you in the exact dimensionality that your ODE is written in, of states, time, and then controls and parameters if relevant. So once that's coded up, and I'll of course give time to let you guys code that up, notice I take the result of integration. We're integrating for 0.2 times hour. So we're wanting to integrate it for 2.2 real world hours, dimensional hours, but obviously we need to non-dimensionalize it. So we're using that hour operator. I see the question online. I will find that in just 1 second and post it. So we're multiplying the 0.2 times hour. So we're actually doing a non-dimensional operator here. And notice we want relative time. We wanted to do 0.2 hours from our initial condition. So the time final section of our integrator call, we do initial condition 1 index 6. So we're saying take the time index of our initial condition and add 0.2 hours to it. So we've got the non-dimensional time. In this case, it's 0, but this is a great format. You can use this format a lot to do relative deltas of your integrators. Is whatever the initial condition is that you're propagating, take that exact initial condition, pull out its time index, and then add the delta time that you want to do the propagation for. You'll then also notice one last thing to point out, and then I'll leave space and time for you guys to just code this up. Notice that after I do the integration, I turn that same variable into a NumPy array. We imported NumPy at the beginning. That is not for anything other than user convenience. That is for nothing other than user convenience. The return of an integrate dense is a list of time histories. But in Python, NumPy arrays can be spliced separately or sliced separately, different from how lists can. So I am in the habit now of turning them into NumPy arrays so that you can do slicing like you see here of give me everything at index 0 of the trajectory. Alrighty. We will tab on over. So we've got an initial guess that we propagate. We see that it's a suborbital hop. But let's say, as analysts, we don't know exactly when we want to do the stop function, or we don't know exactly the time of when this is going to be, or we want to write code that's robust to being handed multiple different initial conditions, all of which are suborbital hops. So let's set up event detection so that we can detect, all right, we're in the two-body model. Let's detect when we have a periapsis pass and stop integration at the periapsis. So for our initial guess generation, it makes sense on the suborbital hop to place our initial delta V, impulsive delta V, at the apoapsis of this suborbital hop to increase our orbit size. So we're going to write an apps event function. So it's a vector function using this format that we're used to. And we're going to make it just return r dot product with V. So when are we having that crossing? 0 for direction. We could, of course, change it to be a negative crossing since we want the apoapsis, but since we're on a suborbital hop, we can set it to direction 0. So essentially, anytime we have an apps crossing with this generic function, it's going to flag as an event detection. And this time we set the stop code to be true because we want to stop integrating when we're at the apoapsis. And once we're at the apoapsis, we're now ready to go apply the delta V. So we're going to create the apps event. Remember, it's a Python tuple that gets passed in your instantiated vector function along with your direction and your stop codes. Let's say we needed to change your event detection tolerance. In this case, it's already within, we've configured it to work with our default tolerances, but here's an example of, let's change the integrator's event detection tolerance to 1e to the negative 13. So here's an example of doing that for if you need to have that exposed to a user. Then we're going to create another integration instantiation where we have the time history and the structure of event detection locations where we're doing the integrate dense again with that same integrator we had. But now we're doing, again, the initial condition's time plus that 0.2 hours. Let's say we want 1,000 points in our time history. And now we're going to pass a list of whatever events we want to do detection. So we're going to pass this apps event into the integrate call so that this IG1 apo should be a time history from our initial condition that gets stopped as soon as we're at the apoapsis of our orbit. And then again, we simply turn it into a NumPy array. This is not for asset functionality. It is purely for convenience of how NumPy arrays can be sliced in plotting.
So what's direction equals 0 again?
Direction, so in event detection, the direction is, do you want this event to be flagged for, because events are always 0 crossings of the vector function. So do you want it to be flagged when your 0 crossing is going from negative to positive, positive to negative, or 0 is, I don't care which direction you go, flag it whenever there's a 0 crossing.
Okay. And then, so this is, so the stop code.
Yes, stop code is, hey, when this event that we're constructing happens, do you want to stop integration as soon as that event happens? Or no, do you just want to record it in this event locations variable?
Okay, so we're going to propagate and then stop that apo.
Yes, so this is, let's say we're trying to write this in a robust tool that can be handed any range of suborbital hop initial conditions, and we want it to, whatever your initial guess is, stop propagation when you hit apoapsis. So for this case, we absolutely could just say, oh, well, we know integrating, 0.1 hour or whatever it is apoapsis, but this is a way to handle a problem if you don't necessarily know in this dynamical environment when an event's going to happen. You just know you want to stop when the event happens. Is you can do this.
Very consistent with SciPy's integrate.
Very much so. Yeah.
Code false with the speed. We do it's going to be the exact same trajectories it was before, but we know.
Exactly. Yep. If stop code was false, it would still propagate that full 0.2 hours. And then if we had an event crossing, it would say, all right, it happened at this time, and here's the states of your crossing. Additionally, if we were in a stable orbit, We wouldn't want to do this with a suborbital hop, but if we were in a stable orbit, we could say, oh, I want to stop after 3 apps event crosses. You could put your stop code to be 3, and it'll record all 3 passes, and then it'll stop after hitting the 3rd.
So stop code, you can just set equal to 3.
Yeah, stop code you can set equal to true or false for, or equivalently 1 or 0 for stop at the first event or don't stop at all. Or if you want multiple of that same event detections and you want a stop after a certain integer number, you can put in any arbitrary integer size to stop after that many passes. So in the CR3BP, for example, I know this, we're in 2-body right now. If you wanted to generate Poincare maps, so you only wanted when a plane gets pierced from one direction, you could set it to propagate some absurdly large number that you're not actually going to integrate all the way out to for your delta time or your time final, and then say, hey, my stop code is 1,000. So propagate this trajectory for this absurd amount of time, but just stop as soon as we have 1,000 plane piercings or something like that.
Oh. Keep integrating until you're absurdly wide.
True. Yeah, or if you don't trigger your events, it'll go to that time. Yeah. Yeah.
But you don't figure.
And another good example is applicable for gateway. Let's say if you're in a gateway orbit, you know the safe zone that you can depart. Then you trigger an event. Okay, now I can depart. And that's
Yeah. Yeah, that's true. Know your safe zone and then say, okay, your event locations that gets returned gives you the exact time and the state of where you're at when you've reached that safe mode or anything, or safe departure region. Okay, so now we're going to set up the initial guess for the first finite burn of this configuration. So you will notice we are going to make a new initial condition 2, I call it IC2, and we're going to copy the final state from that initial guess apoapsis event. Conversely, so to be slightly more precise, you could also use the event location and index into the exact fit of that event crossing. We ran a pretty dense grid, so there's very, very little error between those states in this case, but so you're going to copy the final state of your apoapsis. We're going to get some delta V. So for this, we're going to do an initial guess 900 meters per second. So 900, we're doing this dimensional, multiply it by that capital MS meters per second variable we made earlier. So now this dV term is appropriately non-dimensionalized as a velocity in the non-dimensional velocity terms. But we got to know, we're using a sensical term, and we can picture 900 meters per second, but not necessarily the non-dimensional. Finally, then we're also going to get a unit vector of our velocity. So I'm just doing again, grab and copy the velocity component of initial condition 2. So this is essentially the velocity of that final state, and divide it by the linalg.norm. So that's just NumPy array way of finding the magnitude of velocity. So now we have a unit vector pointing in the velocity direction. And then we can simply say, okay, for our initial condition 2, we're going to modify the velocity components to be equal to our velocity components plus this non-dimensionalized delta V burn that we're doing applied to the unit vector of velocity direction. So then once you've done that, you can go ahead and propagate it out. I change it into a NumPy array just for slicing convenience. And then you can do an updated plot that has both initial guesses, and you should see a circular or a large burn that gets us out of the suborbital hop and gets us actually into the orbital regime. And then one other little test that I have here, and again, this is in the code that was sent with the meeting if you want to just grab it. I have a print statement and a test evaluation of, let's look at the Keplerian elements of this new initial condition here. So I'll give some time to work on that. I also just noticed this. So I've been using asset before it got a lot of its convenience functions. You'll notice in line 122 of this example, cart to kep is the vector function that we defined, right? And it needs the components passed in to instantiate it. Once that vector function is instantiated, I did dot compute and passed in the initial conditions. You don't need dot compute. That's old syntax. You can just do the parenthesis and pass in your initial guess like you've consistently done for all vector function evaluations with real world float point data. So it will work if you do the dot compute, but that is old syntax. It's now more convenient, and the updated syntax is to just instantiate your vector function and then using parentheses pass in the numpy array. Yes, okay, so just to make sure people online get to hear this too, someone was asking in the room on reiterating, what is this dot compute that I did? Essentially, you know, when we went over vector functions in the beginning, I think I alluded to or mentioned, and we definitely in examples showed vector functions, once they're instantiated, they could be passed real world values. They could be passed a list of float points or a numpy array. And if they're handed that, they actually do the computation that's outlined in the vector function. And it says, okay, you know, args index 0 is actually this float point now. So I'm going to do the computations with it, and it returns real world values. But we've also had use cases where we're passing vector function arguments from one vector function into others so that we can stack complexity and stack operators. So now in modern syntax, where you don't need to do the dot compute, you just pass in your float values. Now it dynamically handles and is able to do type detection of, okay, you as a user just handed me, you know, in your parentheses, instead of dot compute, you instantiated cart to kep, and in parentheses, you handed me this IC2 of 0 to 6. So you handed me a size 6 set of floats. So so you instantiated the vector function, and when it's handed floats, it computes and returns a list of floats to you. But it also dynamically handles if you hand it a size 6 vector function where it's not data storage, it's just operators and the result of a previous vector function, it can handle that dynamically and say, okay, I'm going to stack these computes. So now if someone calls that previous vector function, whenever that's handed real world values, whatever comes out of that, it'll be given to me. So we used to have a syntax where you used to have to tell it dot compute for, hey, I'm giving you the I'm giving you an actual float point. I want you to evaluate the actual floats, versus a dot eval of, hey, I'm giving you vector functions. But that's old syntax. It's handled on the back end now, so you can just do open and close parentheses instead of dot compute open close parens.
So that exact same line.
Yep, this exact line.
Delete compute.
Delete the dot compute and just pass in open and close parentheses with the float points, just like we did in day one when we were testing things. Yeah, that's a look behind the curtain of how the syntax used to be before it was able to dynamically handle different types being passed into it. So we'll give just a few more minutes for people to write this up, and then I believe the next slide shows the plot result that you should see, and then we're at 12:30 Central, so maybe we'll take time then to do a lunch break. And ready. Only hearing the response if I'm good. Thanks, Jared. I think we'll just move on to the next slide real quick then. So what you should get provided from that code snippet is you've got a trajectory that we've in our plot got the moon radius. You now fly out towards apoapsis and then launch, apply that 900 meters per second that we are now finally out of suborbital into an orbital regime. And then that print statement on the initial conditions, here's some values that you can evaluate the initial conditions from. I believe inclination is slightly different if you use the initial condition that I put in chat, because that is a slightly different initial condition. But the function evaluation test is here as well. Okay, yes, recording both. Alrighty. So hopefully everybody's back from their lunch break and had a good chance to take a breather, get some food, and if you're back, I'm hoping that you're ready to keep diving in, because we've still got some, we're getting into the bulk of the really good examples here. So a quick refresher in case you know, the afternoon sleepiness has hit, is what we've done so far is we've not optimized anything, but we've used Asset, all the day one stuff that we did yesterday. We've formed the optimal control problems, this time using the pre-written models in Astro. We've instantiated integrators off of that, including our event detection. And we've been able to take an initial condition you were given that propagates out, stops at apoapsis, then does a prograde 900 meters per second burn. There was a comment in the chat. Tim, thanks for flagging that and catching that. I did give the initial conditions that I posted in the Teams chat are slightly different from the initial conditions from what was shown on the previous slide and is in that user inputs. The results will be very close. It was just a small tweak that hasn't been able to back propagate itself back through all of this for a very small components that we'll address a little bit later. But your Keplerian elements should look very close to this. And again, that cart to Kep function even was just a quickly compiled function to drop into this. Once you're doing specific analysis, you'll write whatever vector function arguments your analysis needs. So let's start moving on to constraints, because we've got an initial guess that flies out and then applies a burn. And we said we're going to try to target some semi-major axis constraint. So our next step here is we've got that cart to Kep utility function that I handed you. Let's use that and write a vector function that we're going to pass in the position and velocity states. And that will then get handed through and compute the semi-major axis and return the difference between, oh, the slides aren't shown. Let me reshare. Thanks, Jared. Good catch. Stop sharing and reshare. How about that? Is that sharing on screen now?
I see it.
Anyone? Perfect. Thank you. Good catch. Yeah, this conversation makes a lot more sense if you're able to see the function we're talking about. So what we're doing is we're passing in a few constants from the asset side. So we're going to have some semi-major axis constraints that we're trying to drive the value to. We are gonna need then the inputs that are constants that get passed to the cart to Kep instantiation. So the mu value, the L star, our characteristic length, and our characteristic velocity. And then all we're doing is taking our states, we're instantiating the cart to Kep vector function, and just like you were able to ignore the dot compute. Yes. Yeah, good catch. Thanks. So similar to that previous example where you can just drop the dot compute, you can also remove this dot eval and just treat cart to Kep exactly how you treated any vector functions we wrote in day one. This is, again, syntactically correct. It's just old syntax of running dot eval because we're handing it vector function arguments instead of float points. But that's handled dynamically in the background of Asset now. So this is just a quick constraint that runs our states through that cart to Kep vector function we have, pulls out. Recall we were returning the semi-major axis as the first output of that function. So we're taking the difference of our constraint and our the semi-major axis that gets computed, and then we're dividing it by L star to dimensionalize it again, because that cart to Kep was written for dimensional terms, so we could do quick analysis there. But obviously, our states are non-dimensional, and so we need to have the resulting constraint dimensionalized for our model again.
You get it the way with an RV instead of the states in the KEP call, you just do R, comma V.
Yep,
or would it-
exactly. You could do either, as long as you're passing in the correct number of terms. You could do states, you could do R comma V, you could do VF stack RV. You could do args to list and VF stack all the scalars. I don't know why you would, unless you had some operations you needed to, but yeah, it's very flexible as long as you're working within the sizing. You check online, it is sharing, right? I think I was told yes, but I can't tell.
I'm seeing.
Perfect. Okay. Okay, I know this was only a few lines of code, so I won't leave us on this for too long. So let's advance on to actually getting ready. So these are finally two more constraints that we're going to add. One of them I point out here is the DV cost. Excuse me. The DV cost, which, as we stated earlier, that's going to be between the phases. So the DV cost vector function is going to be used for the OCP, but that's essentially just expecting two velocities passed in, and then exactly like we said, the normal difference of those two velocities. We're also going to write a constraint that says, hey, we're going to take the radius of the moon or some moon constraint and our position argument, and we're going to make the difference between those for an inequal-con. So this is how we formulate a greater than constraint of we're not going to want our spacecraft to dive down below the surface of the moon. We need to constrain it to be above the surface. So once we've written our two final constraint functions we need, it's time for us to start formulating the phases that will go into the optimal control problem. So here it's pretty easy to tell where the best place to put a transition between phases is, because we're flying out ballistically from our initial conditions, and then we're going to go apply an impulsive delta V. So phase 1 is from initial conditions to the burn. Phase 2 is after the burn and going out to the targeted semi-major axis. So phase 1 is obviously pretty simple. You know, we instantiate it with the phase. I used here, again, the syntax of dot set traj. That's where you apply the initial guess and the number of segments. You can also just do that all when you do the phase instantiation of LGL3, comma, IG1 apo, comma, the 1000. This is just equivalent syntax. Then we need a boundary value. We don't necessarily need a vector function for this, because all we're trying to say is, hey, position through time all needs to be constrained at the front of this first phase to be the initial conditions. We don't want asset to optimize it and say, yeah, the best way to get to minimize this burn is to start in the orbit with your semi-major axis and ignore your initial conditions. So we add the boundary value, and then we're going to do a lower and upper time of flight bound. So lower, we're just doing a small amount of time. Again, we're using this, we want 0.001 hours, so we're multiplying it by hours and a maximum of 2. This is just so that it doesn't try to do anything like integrate backwards in time to solve our problem. And then upper, we already know that our initial guess is not going to go out that far, but we're just setting relevant bounds for the problem. And then phase 2, we again set it. Now we can do an equality constraint to the semi-major axis. And we're going to pass in, this is using just the two-body formulation of semi-major axis. So essentially, we want an orbit with an apoapsis at 350 kilometers, because remember, we're using dimensional units are meters in this formulation, and semi-major axis constraint was written to expect dimensional. So we're essentially saying we want an apoapsis of 350 kilometers and a periapsis of 100 kilometers. So that's just a mathematical formulation of the resulting semi-major axis for that type of orbit that we're targeting. So we add that as an equality constraint. We add an inequality constraint to the whole path for that moon distance, and it's going to be our moon plus 100. So we're saying, hey, this whole second phase, never dip below the moon's surface. We know already the first phase won't, because the initial guess and burn are going to happen beforehand, but we don't want the post-burn states to dive into the moon to try and reach our mathematical semi-major axis. And then again, time bounds. So we'll give a little bit of time for everybody to code this up and get this set up in their code. Yeah, there's a good reminder here for the semi-major axis. We're doing a 350 kilometers, so 350,000 meters, plus the radius of the moon, so that it is 350 altitude for the apoapsis and 100 kilometer altitude from the moon for a periapsis. So we had a good comment and question in the room. So when you're formulating this, we have an inequality constraint of the moon distance saying, hey, phase 2, we don't want it to dip below an altitude of 100 the entire time. So how does Asset handle that? If we didn't constrain a boundary value to phase 1 when we later solve this problem, it will enforce this inequality constraint to drive it so that phase 2 gets up to that bound. However, keep in mind, we're right now constraining it to our initial conditions. So if we had, say we try and formulate a problem that uses an initial condition that never reaches an altitude of 100 kilometers, and then we tell the next phase that's going to inherit it of, hey, there's an inequality constraint of don't ever go below 100 kilometer altitude, we have now got an ill-conditioned problem. We have formulated a problem that cannot be met by our constraint. We have conflicting constraints. So when you try to optimize that, it will likely hit 1 or maybe 2 iterations of the optimizer algorithm, and then it will not just return a not converge, it'll say diverging solution space. So as soon as you try to run something and it doesn't even run through the sci-opt scroll and you see diverging, that's the first thing to check is, okay, did I actually formulate a well-posed problem, or are my constraints and conditions that I've applied to these constraints conflicting to where I have a divergent solution space? So
in this case, we use a condition as a boundary value problem, or
Yep.
as a boundary value constraint.
Yes.
For the first phase, and we're setting that inequality constraint in phase 2, knowing that it starts out above.
Knowing that phase 2, to get an optimal solution, phase 2 has to start above that altitude. Yes.
Right.
So it is not satisfying our constraints if it tries to start phase 2 below that altitude.
Right.
So
but we know
it's going to be forced
the end of phase 1. Just
to satisfy our constraints. It will be.
Just
Yeah.
because we know. If you don't know that, and you don't.
Yeah.
And you set that, then you don't necessarily know.
Yes. If you're blindly taking some initial conditions and propagating them, and they weren't specifically handwritten by an instructor for a course, if you just take initial conditions and then start applying constraints downstream to it, yeah, you very well could pose an ill-conditioned problem because you don't understand what when you add the boundary value constraint to all the states, you might not be knowing what you're constraining your problem to be.
Now you could actually allow those initial conditions to change.
Absolutely. Yeah. If this problem was posed differently, if instead of saying, okay, we were kicked off of the, Alan Shepard hit our rocket with a golf club from the surface of the moon and we're stuck on this initial condition, if instead it was, we're designing a small little ascent stage on the surface of the moon, and we wanted to kick off and we needed to go reach these other downstream constraints, you absolutely could say, oh, I'm also constrained in position. I have to start at this specific location on the moon, but I want to have some initial impulse from that because I've got some kick stage on the surface or something like that. You could very much do a problem where you don't bound the initial velocities and see, okay, what's the kick stage have to do to get us to these downstream constraints and targets, or or more specifically, you could say I have a position envelope. You could do this in 3 phases and say, okay, I'm stuck here with some small kick stage, so it's allowed to vary the velocity up to some, let's say, some norm bound of, okay, we've got some like mechanical kick stage or slingshot on the surface of the moon that's able to launch us a little bit, bounded to some velocity magnitude at that point. And then the next phase is a finite burn phase, and we're burning propellant to get up somewhere. And then when we cut off the burn phase, we want to be in some orbit. You could do that as phase 3. We're certainly varying from this example case, but yeah, it's very versatile to however you can pose the problem and write it in a valid solution space. You know, if we constrain, you can't change your boundary values. Also, your boundary values never hit something that's constrained in phase 2. You've now written a diverging. But if you can write it in a convergent solution space, you can pose the problem to vary whatever you need to optimize. Okay, how are we doing on? Do you guys have the code written up for these phases and everything? Perfect. So we've got our initial guesses propagated. We've got constraint functions written as vector function arguments, and we now have the individual phases written and composed. All that's left to do is formulate an optimal control problem now. So it's pretty simple to do here. We can do optimal control problem instantiation. We add our phases in. And again, we are doing an impulsive burn. So we don't want velocity continuity, but we can do forward link equal from phase 1 to phase 2 of position and time, that we do want those to be consistent. Then we're going to add a link objective. So we're making an objective function, adding an objective function that tries to get minimized. And it's going to be that delta V cost vector function we wrote previously. So we instantiate that. We're passing in the back of phase 1 velocity and the front of phase 2 velocity. So essentially now our objective function is, if you recall when we wrote that dV cost function, it's the vector norm difference but between the velocity components here. So our objective function is the impulsive burn magnitude of these 2 phases. This is something, if you wrote just that link objective, you can absolutely run the problem. It should solve and optimize, or I believe our initial conditions are well trimmed enough. You could just run optimize and it should converge. But I'm going to put a cautionary constraint for any of these types of cases. So our objective function, recall, our objective function is a scalar and it is the normal of a vector, right? We're taking the difference of velocity vectors, and the objective function is the norm of those. So remember, we talked even earlier today on this. SciOpt is written to handle analytical first and second derivatives. Your objective function has an absolute value sign in it. So what happens when the delta V is exactly 0? You now have an undefined derivative. So to confine our solution space in such a way where if it tries to step outside of the feasibility region and do a dV of exactly 0, we're going to do a link inequality constraint and essentially say, okay, the dV cost that you assess, make sure that that is greater than 1e to the -6 meters per second. So you can make a trivially small minimum delta V cost, but it's now constrained to stay greater than 0, so that no matter what gets passed into your dV cost, you're passing it into a feasible region. So we're again just doing a link inequal constraint of, as long as you're greater than this, because remember, inequality evaluates of less than or equal to 0. So if we have our limit minus our evaluation of what the dV is, it should always be the result of that will keep us out of that 0 region, again passing in back in front to the dV cost call. So once we've configured that, we can do OCP solve optimize, return the trajectories using the phase objects themselves. Remember, we don't even have to pull it out of the OCP. And I instantiate them as NumPy arrays for plotting again. but now run a plot, the plot call using the previous functions of these new optimized traj1 and traj2, and you should get an orbit similar to this, where you start at it. Our initial conditions we're constrained to, fly up to where we're within the region where it's valid to satisfy things like that periapsis constraint, and then apply a burn, an impulsive burn, which is optimized, but is still hitting the semi-major axis constraint that we applied. So when I ran it on the old data, I got a DV of 864.72 meters per second. You can return this. This should be, I mean, is trivial to compute what the DV is. It's just the velocity difference between the last element of traj1 and the initial of traj2, because that's how we formulated the problem as. And then we redimensionalized it by multiplying it, or by dividing it by meters per second, the meters per second dimensional term. Here's another time to mention this point. By default, assets running that optimize call in multi-threaded. So the threads that your machine has available means that you're going to transcribe the KKT matrix on slightly different threads between runs. So you may get slightly different optimized solutions, but the default KKT tolerance means that your slightly different solutions are going to be, the variance is going to be outside of your tolerance, which is, 1e to the -6th, I believe, as the default KKT tolerance. So it's not like a stochastic approach, but it is multi-threaded. So this is the behavior you'd expect for anything, like IP-opt would do the same. That's why you're getting the benefit of getting a solution in 1 or 2 seconds in this problem. So I'll leave time for everybody to program this up. So in the room, we had somebody run into, when they hit optimize, they got something that said transcription error, and it said size 6, size 7 not matching. Recall your initial conditions to the phases that you're instantiating as need to match the size of states time u, if such things exist, as your ODE problem. So your 2-body ODE object that you're spawning phases off of, expect 6 states and time, so size 7 as your initial guess coming in. Okay, sorry, I see the messages in chat now. We're fixing something in the room. So how I'm printing DV1 right now is I'm just taking the traj1 and traj2, the returned results here. I am just taking so these are just NumPy arrays right now, because we've returned real world values out with the return traj. So I'm just taking the vector difference of the last velocity of traj1 and the first index velocity of traj2, and subtracting those from each other and finding the normal of that difference. I believe you're absolutely right, Tim. That's a good point, that the primary objective right now is the non-dimensionalized V-star. I would caution you, if you are doing single objective optimization, then yes, that prime objective output from your SciOpt scroll, and I believe saved off in your OCP instantiated object, is the equivalent statement, of course, exactly as you said, non-dimensionalized. The one reason I would caution you of maybe writing scripts or anything that just takes that primary objective term is there's not really a flag for if we're doing a multi-objective problem like what we're about to do on the next slide. Then the primary objective is just the summation of all your objective functions times their weights. So as soon as you make you are absolutely correct in your statement. Syntactically, I would be cautious of just pulling the prime objective, because it's if you have multi-objective, it's going to be the sum of all of them. Alrighty, so I think we're set in the room, and unless someone online says to take a break or needs more time, let's move on to a practice where it's your turn to add something. So we walked through that last example. Now we're going to build onto it and do a multi-objective problem. So the challenge is using what we've written so far, let's add another phase. And this phase at the end of phase 2, we're going to add phase 3, and we want to optimize a circularizing burn. So this new phase can be added to the end of your orbit raised burn phase. And then we want to add both those burns into the as objectives to our optimal control problem. So a few hints and guidelines on this. Your new trajectory arc will need a few things, right? Because you're making a new phase. You're going to need an initial condition. So look back at how we generated an initial condition for phase 1 in this example. And that will be a good guideline for making IG2. Once you've got your initial condition, you need an initial guess, which is just integrating your initial condition for some amount of time. A phase will need to be created and added to your optimal control problem, and that phase will need proper constraints and objective. And speaking of constraints, part of this challenge is we're not constraining the final semi-major axis on this new phase. We're going to try and constrain eccentricity. So using the functions and tools we wrote previously, how can we write another function that can constrain our eccentricity as a target? So a few hints on this additionally. Let's see, OCP has already solved 2 of the 3 trajectories in it. So you can absolutely, once you add this new phase with its initial guess, do solve optimize. But this is another use case where just running optimize is probably pretty safe. You're pretty well in the convergence radius for this problem at this point. So that's entirely a user choice. It will drive to the same regions. Additionally, we're going to avoid numerical constraints. So constrain your final eccentricity to be a very small number, not 0.0. Again, because if you look at how eccentricity is geometrically defined, there's going to be a absolute value sign, right? Because we're computing the eccentricity vector from two-body mechanics, and then you take the magnitude of that vector. So just how we constrained our burn, our impulsive burn to go, it can go very close to 0, but not hit 0, so we don't ill-define it. We're going to do the same thing with final eccentricity here. Make your final constraint to a very small eccentricity, not 0.0. And then finally, we're really just trying to constrain the dynamics at that second impulsive burn. So the flight duration of phase 3 that you're adding here doesn't have any time constraint to it like it would if you were doing like this is a phase with a finite burn engine. So in my example and in the solution code that you've been sent, I just add a delta time equalcon to 3 hours so that we can see a full rev. But that time is entirely arbitrary for what you set the time to for phase 3. So let's take a few minutes here. I know this is one step deeper into the pool where we've set up a problem and then walked through it. And now we're going to leave space of if this was your total challenge is to write this 3-phase multi-objective problem. Let's take time to try and formulate that.
So this is adding, so we have what we have and we're adding a phase.
Yep, you have what you have, and you already have an optimal control problem. So you don't even need to recreate phase 1 and 2 or recreate the optimal control problem. You can just create phase 3, append it to your optimal control problem, add any additional constraints to your optimal control problem, and then keep it all running. So here's the versatility of if you solve a simplified problem, you can move on to more complex problems. So definitely, this hopefully is obvious to the people in the room, but also online. This is definitely a time as soon as you feel stuck or feel like you don't know what to do or where to start, please do speak up. This is meant to be an interactive time where you can gain experience solving problems that you formulate in the future. Okay. Running, still have the initial condition wrong. Jared, if you're running the initial condition from the original script, try hot swapping that with the initial condition up higher in chat, and see if that fixes it. If so, then what's happening is Keplerian elements are the mathematical definition of Keplerian elements are close to ill-defined when you have low inclination, as in that initial condition there. So this is the warning, that cart to Kep function that you pulled out of that's not part of the Astro library. That is something I just very quickly took from one example in Velato on one page that doesn't even have quadrant checking in it. That function is not operation ready yet. So if you're going to do things in Keplerian elements, make sure to write a vector function that uses proper formulation. Turn the page on Velato and do the exercise 2, not exercise 1 in that chapter, to make sure that you have things like quadrant checking and that you're well formulated. And an important reminder from the room, make sure you plot the actual trajectory that you converged if you're feeling stressed, saying optimal solution achieved and your solution looks wrong. Okay, so Jared, I hope that kind of sets you in the right direction. So I think we're, just for the sake of time to hit our other examples, going to keep walking through the solution formulation. But definitely feel free to keep working this and see if you can compare at the end here. So the eccentricity constraint looks very similar to the semi-major axis constraint. We're just passing in a different constraint value that we're trying to limit it to. And now it's going to be the first output from that cart to Kep, which, again, reminder, that cart to Kep's not part of Astro. You're going to want to write your own cart to Kep, or even just write vector functions that just compute the the Keplerian elements that you want or need, to do it more of a component entity type approach. So once you've got that, we need a new initial guess and phase. So once again, this second burn, so IC3, we're going to take the very end of trajectory 2. I just guessed 150 meters per second for a burn, compute the velocity prograde, and add your guess magnitude of burn to the prograde direction of velocity. So now you have an initial condition. You can integrate it through your two-body integrator that we already have instantiated to get your initial guess. And then you make a new phase. So the phase just I included that moon distance so that our circularizing burn never should hit that, but because we're satisfying the constraint, there's no hit to us adding it. And an equality constraint on the low eccentricity value that we want. And then, as I said in the tips, I just did a 3-hour delta time equality just to make sure that the final result that we plot shows circularized, but time is very arbitrary in these cases where you're just doing a impulsive burn and the next phase is just the result after the burn. So then we've got the new phase, so we can just take that same optimal control problem instantiation that we've already solved in the first part, append the new phase to it, forward link equalcons of phase 2 to phase 3 now, so again in position and time, add the delta V cost, this time from phase 2 to phase 3, our constraint to make sure that we don't go into a ill-defined region with that absolute value, and re-optimize. So I got a result that looks about like this, and it sounds like, and looks like in the room at least, everybody was getting something around these lines. So you've now solved your first independent problem in Asset. So one last step that we're going to do, if you would like to save time, since I know we're at 2:30 Central now, this is the bottom section of that demo 1 in day 2 of the files. This is just 2 different options or different ways that you could save off trajectory data. Of course, there's nothing stopping you from saving it off in whatever your favorite method is. You could go write a Spice kernel, you could save it to a CSV, throw it into pandas data frames. But here's one example of creating a Python dictionary and essentially getting the time history of each state and time, and then saving it off as a JSON file. Alternatively, a little bit less verbose, but it's a binary file, so That is something to keep in mind when you do pickling. You can also use pickle and just create a dictionary with your trajectory phases. So these are, sorry, not phases, your trajectory time histories. So these are the things that you did return traj to, and then write it into a pickle file to just save it as a binary file on your machine. So this is important to save your trajectory data off because we just solved the simplified two-body problem. So go ahead and take the file format of your choice to save it off. I believe I did pickle files in the next example, and save off your data, because now we're going to do a progressive example of, all right, we've got this lunar problem where we're taking some suborbital lunar hop, doing a orbit raise burn to a targeted apoapsis, and then we're circularizing, but that's in the idealized two-body model. Next, we're going to try and do it in the ephemeris n-body model, where we're lunar-centric, but we have ephemeris perturbations of different solar system bodies pulling actual spice kernels. So you can, if you wanted to, or I guess you could, jump straight into an ephemeris solution of things and just try and ham-fist a solution out in ephemeris, but it's good just practice in astrodynamics in general to start in a simplified model, converge your solution, then jump over to these higher complexity models. So what we're going to do here is save off our time history of these phases. And in this next demo, we're going to solve the n-body problem using these phases as initial guesses for the next step.